Hello everyone, welcome to our group. Our project name is Teaching an Agent to create Mario Bros using reinforcement learning. We have three teammates. I'm Lin Zhenxun, and also Pavan Kumar, and also Anthony Mulier. And our topic, the game we are using is Super Mario Bros. We are using OpenAI Chain environment for Super Mario Bros. On the Nintendo Entertainment System using the NESPA emulator. The goal of this game is to reach the end of each level while avoiding pitfalls and enemies. And the environment we are using include OpenAI Chain environment for Super Mario Bros. Which will provide a standardized interface for developing and comparing reinforcement learning algorithms. And also the Nintendo Entertainment System, which is a classic game originally played on the Nintendo Entertainment System. And also the NESPA emulator to run the NES game within the modern computing environment and integrate it in the OpenAI chain. And this is the environment table for everyone to take reference.
I'm Antoine. Now we have seen how the Mario Bros. Environment is built, so let's see how our agent will navigate it. To help our agent's success in playing, we are directly thinking about the Q-learning concept seen in class. We have seen it applied to the power balancing problem or grid world. To summarize the algorithm, the Q-learning matrix stores the estimated value of action A and state S. At each step, we calculate the error and correct Q. We also saw that this method was limited in complex case, and Mario Bros is a very complicated one. The main problem with the method is that the tabular Q-learning can't handle Mario's enormous continuous data space, so we need a function to approximate that generalized across a familiar field. So this is the Deep Q-learning network. It replaces the huge problem matrix with a neural network that learns the most important information by itself without storing it all. QSA became QSA theta, and theta are the model weight. Here is how the new algorithm works. We observe the states. We predict a Q value for all action. We select action via E-grading expression. We receive reward and the next state S plus. We store the transition in memory, and we sample a mini batch and minimize the zero. In your Mario project, we process each frame, tag consecutive frames as input, and train the DQN and on 1,000 of transition. At the end of a long training session, our agent know more or less how to play. We also train an agent with a double deep Q network method. In double deep Q network, we don't change the algorithm, but two networks are used instead of one. The main theta to choose the action, the other one target theta minus to evaluate it. It reduces the overestimation of Q value and stabilizes the learning. As a result, learning is more stable and Mario has a less erratic behavior.
My name is Pavan and my student ID is 313831002. Now let us look at the training performance of DQN versus DDQN. You can see in DQN that there is no high reward and the reward is stable as all the episodes increase, whereas in DDQN you can see that it tries to learn and go for the higher reward along the episodes. The exploration schedule of DQN versus DDQN. So the exploration schedule of DQN is stable or mostly fixed, whereas the exploration schedule of DDQN decreases, which says that it is learning a better. Let us look at the demo. So the DDQN's train. So the model is training now. Let's look at the test. So we run the test for 10 episodes, and you can see that the total reward of DQN is 680 and is consistent for all the tests. Let us look at the DDQN strain. So DDQN has different rewards for each episode. And test of DDQN. We can see that DDQN has the highest reward of 1923, which is almost 3 times of DQN. Thank you.